Okay, so in the first part, we have seen how mass spectrometer works. So if you haven't seen that, I'd highly recommend that you go back and see that. So from the first part, we know that the sample needs to be ionized. The reason it needs to be ionized is because inside the mass spectrometer, there is total vacuum. Like you have no air. You cannot have anything in there because air is composed of gases. Those are molecules. And if you leave air inside, what's going to happen is that your detector is going to detect those molecules as well. So you don't want that. You just want to detect your particular sample. So that's why it's always a vacuum inside. So if it's a vacuum inside, you cannot pump any other gas to push your sample to the detector. So the only way that your sample can travel inside the mass spectrometer is by making it positive, by ionizing your sample. So once your sample is ionized, what's going to happen is you can have electric plates, right, which are negatively charged. So your sample is positively charged, so it's going to get attracted to the electric plates and it's going to accelerate. So that's how it gets inside the mass spectrometer and it keeps on accelerating because there's nothing to stop it. You don't have any friction inside, right? It's vacuum. So that's that. So the way this thing happens is because is say you have this particular molecule. Say you have CH3 CH2 OH. So you have this molecule. So what happens is, say, around the oxygen, you would have two lone pairs of electrons, right? So the the electron from this electron gun inside the mass spectrometer, which is used to ionize your sample, what it does is it throws randomly, it throws high energy electrons. It throws high energy electrons into your sample, right? These are high energy electrons from the electron gun. So what they do is they knock off electrons from your sample. So this particular electron on the oxygen is knocked off. So what happens is this in turn produces a molecule that looks like this. That looks like this. So this whole molecule is now positively charged, right? This whole molecule is now positively charged. So now it will get attracted to the electric plates, and it would accelerate. That's the idea. So when this guy goes into the sample, you know that this guy's mass is what? Let's calculate. 12, 15. Let's just calculate faster. So you have two carbons, so that's gonna be 2 times 12 plus you have 6 hydrogens, so that's gonna be 6 times 1 plus you have 1 oxygen, which is 16. So this is 24 plus 6 plus 16. So this is gonna be 46. So the mass is 46 grams, right? For grams per mole. And the charge is plus 1. So this is gonna be 46 mass divided by plus 1 charge. So this is, we'd call this 46 m by E, mass by charge. The reason we call it mass by charge is because this deflection by the magnetic field here, which is very crucial to this. Again, if you haven't seen this, it is highly recommended that you go back and see the first video I did on mass spectrometers. So if your sample has more than one positive charge, it's going to be deflected way more than usual by the magnetic field. So the magnetic field affects the charge is the charge on the sample and the mass of the sample determines how much it would deflect at a particular strength of magnetic field. So that's very crucial. So that's why we use mass by charge. So it is also possible because this ionization process by the in the ionization chamber by the electron gun is very random. So it is also possible that another electron from the gun would come and knock the other electron off. So in that case, what you would produce is you'd produce the sample with two positive charges. So in that case, your M by E would be your mass was 46. Your mass was 46, but now the charge is plus 2, right? So now what you produce is 23 M by E. So you'd see a peak at 23 M by E as well. So if you have a mass spectrometer, let me change the color here. So okay, so this is how it looks like. So the data in a mass spectrometer, like this is what the data you would see. You'd see a plot that has a x-axis and a y-axis. I cannot draw. Please excuse me with that. So the x-axis is M by E. In some cases, they might say M by Z, but don't worry about that. And this is the relative abundance, which means abundance means how much of it do you see. So this is basically how much of the sample was this guy, how much of the sample was this guy. So that's the relative abundance. So when I inject this sample into the mass spectrometer, what happens is I'd see a 46 M by E. So let's go and draw the peaks there. So I'd see a peak at 46. So this is 46 M by E. Don't worry about the height now. We're not going to talk about the relative abundance now. We're just going to talk about where we see the peaks, okay? But this height would be different. So, and then we'd see one at 23. So somewhere here, you'd see one at 23. You'd see one at 23. And then there's something else too. It's called fragmentation, right? So, like I've said, so this is your sample. So this is your molecule. So this is your molecule. And let me just draw the bond of the OH separately, okay? So this is the OH, and let me draw this bond. What are these bonds? These bonds are basically electrons shared, right? So you have a pair of electrons here, one from the carbon, one from the hydrogen. So in this bond, you'd have a pair of electrons, right? That is forming the covalent bond. So for that pair, you would have one electron from the carbon and you would have one electron from the oxygen. So let me just color code that. So say the blue one is from the carbon and the green one is from the oxygen. Can you see the colors? Okay. So the green one is from the oxygen and the blue one is from the carbon, right? So if, unfortunately, if for some reason the electron from the electron gun in the ionization chamber, that is a complete random process. So it is very much possible, excuse me, it's very much possible that the random electron knocks off this electron. This was the electron from the oxygen, right? So what would happen now? So now you would produce. So now you would have this bit is okay. So this thing. So as this electron is gone now, this carbon cannot share its electron with this oxygen. So what would happen is this carbon would take its electron back. So this carbon would take its electron back, and this would become a free radical, right? If you do not know what free radicals are basically uncharged and species with unpaired electrons. So this guy is uncharged and it has an unpaired electron. So this is a free radical. And then you would have the OH. But notice that the OH lost its electron, right? Because its electron was knocked off. The electron that it used to bond with the carbon is knocked off. It still has the lone pairs of electrons. Okay, let me put the lone pairs of electrons just so that you can see. So you would have one lone pair of electron here, another lone pair of electron here. The oxygen still has those, but it nonetheless it lost its electron, right? That it used to bond with the carbon, so that's gone. So what would happen now is this guy becomes positive. Now, this molecule, this fragment. So we call this fragment. So this is a fragment. So this fragment is now positively charged. So as this guy, as this part, this is also a fragment, but this fragment is not positively charged, right? It has no charge. So this guy will not accelerate, will not get into this guy, as it is not charged, it is not affected by the electric plate. So it doesn't accelerate towards them. So it doesn't get inside the mass spectrometer. But this guy is positively charged. So this is positively charged. So only this OH plus fragment accelerates towards the inside the mass spectrometer. So what you would see is, as it got only one of its electron knocked off, so you're gonna see a mass. So this guy's mass is what? 16 plus 1, 17. So you would have 17 mass divided by plus 1 charge. So you would see a peak at m by e 17. So you're gonna have another peak at m by e 17. So these are fragments, right? This is a fragment. This is not a fragment, but this is a fragment. So as this is a completely random process, you would produce different fragments, right? You can break this bond here. These electrons can break this bond here and produce a fragment and produce a CH3 plus. This process is so random, it can also produce a CH2OH plus fragment, and this would be a free radical at that point. So what I mean is, say this guy, say this electron, this random electron didn't hit this electron of the oxygen. Say it hit, let me erase this bit. Let me erase this bit. Oh, that's too small. So yeah, okay. So say that this electron went and hit this electron. This was the electron from the carbon that was used in the bonding. So what would happen now? So what would happen now is, so as this carbon lost the electron, so as this carbon lost the electron, so we're gonna have a positive side on this one. So you have CH3. So you would have CH3, CH2, and this guy lost his electron, so there's a plus. But the oxygen didn't lose an electron, so it's going to take its electron back, and the OH is going to become a free radical now. So the OH becomes the free radical. I'll draw the electrons there. So this is the oxygen's lone pairs, and this is the electron, unpaired electron. So this is, so in this case, what happens is, so in this case, this has no charge. But this guy is my fragment, and this has a charge, right? So if I calculate the mass, I have 2 carbons, so that's 24, and then 24 plus, I have 5 hydrogens. So that mass is going to be plus 24 plus 5, that's 29. So my mass is 29, and my charge is plus 1. So I'm going to have a peak at 29 m by e. So I'd also see a peak around 29. So these are fragments. So notice how the highest mass, not the tallest, okay? Not the tallest. This is very important. Not the tallest. The highest one, okay? So let me choose a color here. Okay, done. So the highest m by e, highest m by is the most to the right. The highest m by e. The highest m by e is basically the peak for the whole molecule. It is not fragmented. So the highest m by e is called, well, it's called intuitively the molecular molecular ion peak. So basically this means that this is, as it's the highest, there's no way it has been fragmented. So this has to be the molecule's mass. So in many cases, this is the most important peak we deal with, but in some cases, fragments are also important when we are comparing, when say I have two possibilities of what a sample is. So the fragments will give us more detail about what that sample is. I'm going to go into that. I'll create a third part for this. So I'm going to talk about that there. So this is basically an introduction to what a molecular ion peak is. So again, I'm telling you that the molecular ion peak is not the highest one. I don't care about the abundance. So as it's a probability, it could happen that the 17 peak is the highest. I don't know. So okay, let me figure that out. So this could have been the highest peak. It doesn't matter. We don't care. We don't care about the height. We have nothing to do with the abundance. It might be very tempting to go with the highest one and say, oh, this is the market. No, don't do that. Hold your horses. So what's going to happen is the highest M by E value, the most towards the right, most right, okay, is your molecular ion peak. So just remember that and you should be fine. So I'll make another part of this video later on.